Okay, hi everybody. It's Ethan Adkins. It's June 2018, and I'm going to do a video about the basics of fractals. So I'm not really going too in depth about deep mathematical formulas involving how to bring into fruition fractals. But I'm just going to talk about what are fractals, fractals applications, different types of fractals, the elements of fractals. Fractals are a really interesting concept and element within our universe, and it's something I thought was really interesting, so I made a brief video about it, brief presentation about it as well. So let's dive right in. So first question is obviously, what are fractals? And fractals are a branch of mathematics extending into a form of art and science. So fractals can't really be pinned down to one area of profession that people have. It's mainly obviously a branch of mathematics, but it can extend into art and science. And as I'll go on later today in the lecture, it also goes into biology, genetics, construction of DNA, other aspects of art, and astronomy. So it uses geometric shapes and equations that do not adhere to Euclidean geometry. So basic Euclidean geometry is basic dimensions: 1 dimension, 2 dimension, 3 dimension. Three-dimensional shapes and figures, geometric figures, a straight line, a circle, are basically laws of Euclidean geometry. And basically fractals can provide mathematical explanations about the formation of organisms and geography. So that's one of the applications that fractals have been able to extend our understanding of organisms and geography. So there's two different kind of elements of fractals. One is self-similar dimensions and non-integer dimensions, which are sort of very similar. So self-similar dimensions are an element of fractals, and it's the ability to magnify on a shape or dimension, and the shape or dimension contains its original structure and therefore is self-similar. So if you look on the right, there's a fern leaf. If you were to zoom in, magnifying the fern leaf would look similar, because it's a self-similar dimension. The leaves on the fern leaf have the same geometric shape and geometric dimensions of the fern leaf itself. So the farther you zoom in, magnify on a dimension, the dimensions within those magnified through the geometric shape are self-similar. So you can see here, it's like a right triangle. It's a regular equilateral triangle. You zoom in more, because it's still an equilateral triangle. If you zoom in more and magnify more, it's just composed of equilateral triangles. And this is Sierpinski triangle, which is probably one of the greatest examples of a complex fractal, but also a self-similar dimensional fractal. So you can see if you were to continue to magnify on this fractal, you would still see the same equilateral triangle as you magnified the view. So you can see the same structure at different scales. That's kind of the whole point of explaining self-similar dimensions, that a fern leaf, Sierpinski triangle, and other aspects of fractals have self-similar dimensions. That's a very key part of understanding fractal dimensions, is that they're self-similar. And the second element is non-integer dimensions, which are dimensions composed primarily of whole numbers between 2 and 3, and they're also composed of numbers that are mainly 0.4, 1.4, 1.8, and 2.6. So these dimensions are usually between two whole numbers. It doesn't have to be 2 or 3. They're two whole numbers. So this breaks the laws of Euclidean geometry, which pertains to basic one-dimensional whole numbers and one-dimensional planes. So you see on the left, Euclidean dimensions, a point is considered a 0, a line is 1 dimension, a regular two-dimensional rectangle, that's just 2 dimensions. And then when you get to 3-dimensional figures, you look here, you can see that's a 3-dimensional cube. But when you get to fractal dimensions, they're broken up and it gets much more idiosyncratic and interesting. When it gets to 0.4, so it's broken up, dotted lines, 1.4, 1.8, then 2.6. So it just talks about how fractals pertain and ascertain and adhere to certain fractal dimensions, their own dimensions. They don't adhere to Euclidean dimensions that are very basic. Euclidean dimensions are mostly the basic dimensions that we as humans adhere to on Earth and in the universe. And so this is obviously on the right, you got length is 1 dimension, area 2 dimension, volume 3 dimensional. But fractals, on the other hand, do not adhere to these Euclidean geometry rules. So that's what makes fractals so interesting. So you can see that they can adhere to different fractal dimensions that are between a whole number, 2 and 3 usually. And so we'll talk a little bit about complex number fractals. I won't really go too in depth about what these integers and what these exponents mean and how they can be executed in order to make a fractal. But I'll just go a little bit in depth about Benoit Mandelbrot and Gaston Maurice Julia, who are the two founders of fractals as we know them today. And they obtained this knowledge through iterations and rational functions. So rational functions are just algebraic functions, right? Just basically a numerator, denominator with exponents. There's multiple of formulas that adhere to rational functions. I won't go in depth about rational functions too much. And but mostly iterations, cycles. So these are the two kind of main aspects that make a fractal the way it is iterations. By using iterations and rational functions, Gaston Maurice Julia wrote multiple books on iterations and rational functions, which Mandelbrot later extrapolated on and was able to make the first fractal in the 1970s. He was an employee. Benoit Mandelbrot was an employee at IBM in the 1970s, and he took great influence, obviously, from Gaston Maurice Julia by taking influence from his qualities and his interest and achievements, observations of iterations and rational functions, and was able to project these iterations and rational functions together along with his own formulas: Zn equals z squared minus 1 plus c, z equals a plus b times I, which is an imaginary number, non-integer formulas that point out the coordinates for where the fractal will lie on. So he was able to make the first fractal on a computer graphic on an IBM computer, thus creating the Mandelbrot set using iterations combining the Julia set properties. So Julia set properties are inextricably linked to complex number in the Mandelbrot fractal image. And basically these formulas, in essence, are just the coordinates of where the fractals would be, on a plane. Not a Cartesian plane, but a simple horizontal vertical plane. Very similar to Cartesian plane. So they both are infinitely complex and rely on imaginary numbers. So z is usually for coordinates, and an iteration cycles through z equals z squared plus c. And as you can see down here, it talks about the genetics of fractals and how certain integers, once inputted, can change the color, can change the positioning, can change even the density and volume of certain fractals. So here's just a basic picture of the Mandelbrot set. So as you can see, the x, it has an x and y, and the z-axis, z, negative z, negative 1, 0. And once this is placed on an axis, on a plane, you can basically it's like a blank, it's like a tabula rasa. This is a blank slate for a Mandelbrot set to be configured and changed and deviated from. But this is the basic set: Cn equals z squared and minus 1 plus c. Which, once you plug in actual integers into these formulas, it stops becoming just mathematics. It becomes actual art. As you can see here, once you add in these different configurations, you can add color. And I'm going this is very basic. I'm not going to go into the formulas themselves. This is just the formulas enabled to enact these fractals. So z equals a plus b times 1 times I, and then the same one, z1 equals z squared 0 plus c, which are integers within themselves. But these are just, this is a blank slate for what the basic Mandelbrot set is in a fractal. And I will go over more about the mathematical, technical, idiosyncratic aspects of the formulas pertaining to fractals and Julia sets. But right now, really basic, really basic. Just this is the overview of fractals. So Julia sets, as you can see, they adhere towards Mandelbrot sets, but they also couldn't exist, and vice versa, could not exist without Mandelbrot sets, along with Mandelbrot sets cannot exist without Julia sets. They're inextricably linked together. And as you can see here, it's pretty interesting how different, once you zoom in on certain aspects of fractals, they give you these shapes right here on C2 and C1. But C1 overall is the Mandelbrot fractal. the elementary fractal as we know it. So I'll talk quickly about iterated function system fractals. So these are just the steps of making an iterated function system fractal. So you have to define a set of plane transformations, drawing an initial pattern on the plane, any pattern. So this doesn't have to be triangles. It can be circles. It can be rhombuses. It can be trapezoids. It can be spheres. It can be cones. And you transform that initial pattern using transformations in the first step, transforming the new picture, combining transformations, repeat the fourth step. So this is when and then repeat the fourth step as n of initial and transform patterns, using the same set as many times as possible in theory. This procedure can be repeated an infinite number of times. So that's what's interesting about fractals, is that it really does deal with infinity and the concept of making infinite, iterations and using rational functions. So that's where the iterations come to play, and how this can be extrapolated and iterated for time, and by use of iterations and rational functions, we're able to make these infinitely complex, iterated function system fractals. So this is a Sierpinski triangle, which is the classic example of an iterated function system fractal. So we'll talk about this presentation is almost over. Really, I'll talk quickly about fractals in the universe. So how fractals can help humans understand the repetitive nature of cycles of iterations and hierarchical structures in the universe. So we can really have a firmer understanding of spindle fibers and spiral galaxies and other aspects of humanity and the universe as we know it through the use of fractals using iterations and rational functions. So it's pretty interesting. And with my last slide, I talk about how fractals can be applied. Fractals can be used primarily in computer science to generate computer graphics, landscapes, and intricate models of geometric figures in reality. Can be illustrated using these formulas on a computer. So, basic CGI can be used through the use of fractals, and iterations can be used to make what something seems like. You take a CGI model of a person and use iterations and rational functions, expressions to make that person multiply and seem infinite. Those are, elements of fractals. And it can be used in film. It was used in film to construct the Death Star. If you look closely on the right, you can see those aspects of the Death Star. If you zoom in closely, it becomes these infinitely expanding little tiny, the centers, atoms, and blocks, if you will. But this is sort of what the basics of fractals are, is that they can be used in a multitude of aspects of life. For film, for science, especially science. Scientists have had a better understanding through the use of fractal geometry, had a better understanding of DNA, exonucleic acids in biology, and the substructures of chromosomes that have been found to have fractal-like properties. So the genetic material in chromosomes, there's 23 chromosomes, 23 pairs, 46 individual chromosomes. They've been able to link chromosomal substructures to have fractal properties. Because if you magnify on chromosomal substructures, they retain and remain their original shape and geometric structure, which makes it really interesting. And now I'm going to briefly go on about just looking at a fractal and how we can play with a fractal. You can do this yourself anytime you want because it's free. So let's see here. I have an online fractal generator. I'll show you what I mean. Kind of cool thing about this. So we have a quadratic Julia set right here. Let's do a Mandelbrot set. And if we just hold shift and zoom, we can see different iterations and different magnifications of a fractal. And as you can see, it relies on real value, maximum, minimum real values, maximum imaginary number, minimum imaginary number, value, scale, and render time. So let's just reset it. So let's go back to the basic. Yeah, so this is a basic Mandelbrot set. And it's pretty interesting if you zoom in on here, it has very similar properties to what Julia sets pertain to. It's just interesting, right? It just continues and continues. And these look kind of like the fern leaf that I showed you in the earlier slide. How these continue to expand and expand and expand over time. And basically infinite. I'm actually curious if I can, I can't deviate from what has already been shown here. But there are multiple different platforms you can make your own fractals on, such as Shader Toy or Chaos Scope. It's pretty interesting. It's just fun to look at, really. But it's also an art form. But it shows how mathematics doesn't have to be esoteric, idiosyncratic fields that some people just can't understand. Fractals aren't that hard to understand. And once you do have a basic understanding of it, just a basic understanding of it, it's fascinating how infinite fractals can illustrate the universe. So let's see, we'll zoom in somewhere else. So isn't that pretty cool? You can see that it still pertains to the Mandelbrot set, even when it's magnified. So anyway, yeah, might do another video about fractals. Fractals are pretty fun. Yeah, and I might do more in depth about the technical kind of aspects of fractals and how to make a fractal maybe. But other than that, I want to thank everybody for watching, and I'll be making more videos in the near future. Thanks.